let's get things rolling. Welcome to office hours of Friday, November 19th. Let's announce that we are streaming now. Oh shit, I forgot to pull up the chat. Crap, people are chatting unsupervised. Boom. All right. Pulled up the chat. Okay. Awesome. All right. Let's see who's on. We got like 6 people on so far. How's everybody's, let's actually first check in with how everybody's doing with baby kernel. Let's see what we got. Scoreboard. It looks like we have 3 full completions. Trees, Naughty Boy, and Aiden Herja. Great job. Let's see how far people are making it here. Wow, nice. 57, 55, 45, okay. All right, this is a massive dip from level 5 to level 6. Wonder if we should go over that. And then from there, let me see what I'm being texted. All right. Cool. Okay, so we have a 20-person drop from level 5 to level 6, an 8-person drop, then 9-person drop. Okay, and then slow drops. So that's how typically we identify massive drops. Places where we need to insert new levels. Obviously, we won't insert new levels. Let me fix this camera so I'm more in frame. We won't insert new levels on you partway through, but something to keep in mind for future students. All right, let's go quick through the meme review, and then we'll roll into the class again. I wasn't able to, god damn it, why doesn't that work? Wasn't able to do class last time. I apologize. But yesterday, but now we're rolling onwards. All right. So we are almost done with class. We have one more module launching next week, and then it's that module on that's like the final module. We'll just chat and chill and have a lot of fun catching up on challenges for the rest of the year, and then it's over. That's it. Nothing left. All right. Last time we ran into a very, very upsetting situation where I was crawling through in the debugger what turned out to be linker code calling puts, which was pretty awesome. I just wanted to show you stepping into a system call, but instead we were suffering. But it's okay. We got through it. It just took a little while to understand what was going on, and that's what it's always like. You just have to understand what's going on, and then you can hack it. Basically, hacking is just understanding things really, 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 really well. Boom, done. All right. Otherwise, I hope you've all been enjoying kernel concepts. 3:30, I guess, is our operating systems course at ASU. It would be curious. I'd be interested in seeing if people learned more in 3:30, taking it as students, or more trying to hack the kernel in in 466. I guess there are different concepts that are taught, but I think by doing pwn.college, you pick up some idea of signals or signals of operating system concepts such as scheduling and how the kernel works and user space, kernel boundary, system calls, signals, all of this fun stuff. That's actually mostly how I learned operating systems. Hopefully it's useful for you as well. All right. Hopefully also you're enjoying our new kernel setup, because that's been very cool to see working. All right. Otherwise, if you smash your head against these challenges enough, they will eventually break, or your head will break. Just remember, you can power up quite a lot by using GDB. I don't think you can not use GDB in these challenges. So much stuff is dynamic in nature, where the kernel decides to place modules, where the kernel decides to place buffers. All of this stuff tends to be very dynamic. You'll need GDB to survive. So don't forget to debug things. Then this amazing meme is pretty hilarious, but yeah, check this out. It was awesome. That's very true. I forgot to make tea. I didn't have time before class, which is quite unfortunate. Oops. And I realize I'm blocking off part of the meme. Hopefully you don't. Hopefully pwn.college doesn't drive you to the bottle, but it's a good series of video memes. These video memes, they're pretty new. I don't remember them existing last year in the in our class, but this year it's a good set of video memes that we can, maybe at the end we'll have like a best of the semester meme lowdown. That could be cool. All right, yeah. So as someone stated in the Twitch, the life of an ASU student sounds like great fun. How do I get out of this? I always get stuck. All right. Finally, remember, Toddler 2 is coming. I know a lot of people are starting to really hit their limit and hitting module after module after module, but we're almost done. You finish up baby kernel and you have Toddler 2, and then just going back and reviewing stuff. Excuse me, I'm going to blow my nose. All right. You're almost there. Just power through a little longer and you'll be out the other side, maybe with a blue belt. That'll be super, super fun. Okay. Cool. Otherwise, while you're waiting for Toddler 2, remember the kernel is due in 4 days on the 22nd. Yep, for full credit at 4 p.m. Otherwise, half credit until 12/12. And then let's open it up for questions. If people have questions, I'll answer them. Otherwise, I will go and take a look at level 5 and what's so tricky about level 5 that we are losing a significant chunk of the students. I'll look at level 6 and see what is tricky about level 6 that we're losing a significant chunk of the students that were able to solve level 5. Overall tips for debugging. Breaking and stepping is painful. Breaking and stepping is painful. Let's see. That's what you gotta do. You gotta break, see what's going on, step, try to understand. Use the source code of the kernel, the way that it's set up in Jeff and Pwn Debug. It'll actually print it out for you, and that's super useful. Otherwise, you just have to build up that debugging skill, build up the intuition of what is going on from experiencing different ways that code fails. Okay, 7 and 8. So let's take a quick look at 6 first, and then we'll take a look at 7 and 8 and what is going on there. Okay, so let's download 6. Clean up from last time. All right, let's download 6.1. We'll start in practice mode. All right, and then let's open up where is it? There we go. Let's open up the kernel module. Where'd it go? There it is. 6.1.ko. I really need to disable that, delete the mini dump. All right. Load dwarf debug information. Not all entries were possible. Okay, here we go. So we have a pretty straightforward module. We have a device open, handler, write, release, an init module, clean module. Init module looks like we use vmalloc. What the hell is vmalloc? Well, if we don't know, we can always Google for it. So we go in, we say Linux kernel vmalloc. We click through vmalloc. It says allocate virtually contiguous memory. Okay. So, allocate enough pages to cover size from the page level allocator and map them into contiguous kernel virtual space. Great. Let's go back to IDA. So here we are basically allocating memory of size 4096, one page. Then we create a proc file called pwn.college. We provide this file operation struct, which has the device write handler, device release handler, and probably, I'm guessing, the device open handler was just somehow not detected, but it's there, and we can probably debug and in GDB figure out that that gets called when we actually open the device. So okay, so one thing that happens is, and since this even has symbols, we see, okay, shellcode is what it allocates, so that's going to be shellcode, presumably, that we can write somehow, and we're able to allocate it. Okay, then, okay, check this out. We read the wrong man page. Man page says, for tight control over page level allocation protection flags, use vmalloc, and in fact we do have a single underscore vmalloc that we're calling there. That's what we're actually calling. I'm guessing this allows us to make the memory executable. But anyways, let's just assume that that is shellcode memory that's executable. Move on from there. Then prints a bunch of stuff. Great. One thing it prints is, let's do here, we say turn this into a string. Okay, so it prints hash hash hash, and then the next thing it prints, print k takes it can take a log level, and then it takes the string. So here we say, okay, welcome to this kernel challenge. Awesome. And then log level and string. And then another hash, hash, hash. Okay, cool. So basically we welcome, no useful information there. All right. So then the rest is, one is cleanup module. Nothing happens when the module is unloaded. It just removes the proc file. So now proc open, nothing happens. We're down to write and release. So on write, we seem to basically copy from user into the shellcode buffer from the buffer that we pass in with the write of size v6 and of offset. We can break here, but this is the offset into the file. Oh, that we are. I wonder if you can seek directly into that offset. That would be interesting. Anyways, the offset into that proc file that we're currently working with. So we are. Oh, that would be a very cool level. Hold on, let me write down. Let me just write down this level idea. Oh, okay. Connor's thinking about it. Connor, can you write down the level idea? Basically, using the offset, whether through multiple writes or whatever, to overflow this buffer more trickily. All right. So, what are we doing here? We are reading in shellcode, and then we just call it. Okay. So obviously this shellcode has to be executable, or this would always crash. And this seems, at first glance, quite straightforward, right? We read in shellcode and then we call it. So of course, what do? You remember baby shell. You remember, okay, in baby shell I called open, read, write. So let's give that a try. This isn't going to work for very, very good reasons, but let's at least show you why. All right. So first, let's create the shellcode. Do we already have some open read write shellcode? Okay, open at read write. Let's just adapt this to open read write. So we're gonna open is 2 RDI is the flag file, RSI is 0, boom. Okay, so open, read, write, exit, and we are opening /flag. Okay, here we go. Gonna compile and grab it. And all of this is gonna be useless in that because this isn't the correct approach. All right. So we can execute that elf file, and that shouldn't have happened. What? Oh, I had commented this out. Okay, perfect. All right. Boom. Okay, perfect. This should have exited 42. And if we run this as root, awesome. We get the practice flag. Okay, so my open read write shellcode works. Now, we dump it out. Here it is, nice and simple. So what are we gonna do? We're just going to VM connect. Let's bring up the logs here. it's starting up. This is, as we saw, logged by a kernel module. Okay, perfect. We're in. We have proc pwn.college. Perfect. And then what we're going to do is cat orw.bin to proc pwn.college. And that's our open read write shellcode. And we segfault the process. So this is cat segment segfaulting. And the kernel logs a bunch of angry shit. And it's saying, wow, it's really upset. Yeah, it seems really upset if we scroll. Okay, what the hell? How can it be this upset? Okay, let's go to the beginning of it being upset. Boom, bug, stack guard page was hit at blah, blah, blah. Stack is blah, blah, blah. Kernel stack overflow, basically, and then there's a big crash. The code at which it crashes is this D0482500F0. Is that our code? Just out of curiosity. No. All right. So anyways, it crashes us some code, but basically we hit a bug in the kernel. Cat segfaults. When exactly does cat segfault? Well, we can actually strace this. Cat segfaults at exactly when it writes the shellcode to standard out, which is redirected into the pwn.college proc device. Why does cat segfault? Oh, interesting. It's double logging. Cool. Okay, anyways. Well, cat is segfaulting because we are executing shellcode directly in the kernel, but that shellcode is written for user space. A user space application makes system calls. And that system call will context switch into the kernel, and the kernel will handle the system call properly. A kernel thread, which is what this is, what runs this, is on the other side of that system call. When that kernel thread makes another system call, really bizarre stuff happens. The kernel shouldn't make system calls, but I think that, let's actually trace through it, I think that GDB will, or that Linux will helpful, or Intel, I guess, x86 will helpfully allow it. Let's take a look. Speaking of how to debug this, right? So we have our open read write shellcode. We're literally going to GDB bin cat inside the kernel. No, outside the kernel. No. All right, let's not actually use bin cat. We're going to use a launcher file. All right, and we're going to open proc pwn.college. Don't forget to open it in a writable mode. We're going to read in the shellcode. Whatever shellcode we give. Sorry, I'm a little discombobulated. The text is a bit small. Oh shit, the terminal. Fuck, I forgot to make it full screen. Are you serious? Oh, no. I switched out and back in. Okay, we're good. Phew. Alright. Here we go. We're just writing a quick launcher of our shellcode into the kernel. Opens up proc pwn.college, reads in our shellcode. Let's read in the shellcode first. Okay. And then we're going to open this guy up. We're going to write fire so we know that things are happening. And then we're going to write to this file descriptor from Shellcode of the exact size. Okay. This should be awesome and should get us everything we need. All right. And if you recall from my lecture on Tuesday, we're going to make this not no pi file so that it's easier to break in GDB, to break at a place inside this file from outside of the kernel, because we know the virtual address if there's no position independent code. So no pi at launcher.c. Let's just remove all of the warnings, just one thing less to worry about. And then we'll launch our open read write shellcode directly into the kernel, fire, sec fault. Okay, if we strace it, we know where the sec fault happens. It's at this write. And of course, our logs are screaming at us in panic about crazy stuff going on. And things look pretty corrupted, right? So especially because there seems to be an infinite amount of page fault, handlers, and then there was, stack guard page hit, the same sort of thing, right? The stack guard page being hit, that's a really bad news. Probably something very bad happened. Okay, so let's see from the outside what happens when we do that. All right, so we're just going to see real quick. We're going to obj dump -d launcher. Where's fudge? Sorry about making you read the wrong format of assembly. All right. In main, it'll be at this write. So this write is what ends up triggering the syscall that crashes. We're going to break there, but we're going to do it from outside of the virtual machine, debugging the entire VM, including the kernel, right? We're going to break here, continue. Here we're going to do our launcher, open rewrite that bin, and we're in the breakpoint. Awesome. So we're right now running this open rewrite that bin, and we're just going to step until we hit the syscall instruction and see what happens. Oh man, sorry. One thing, we were just stepping through linker code again. That was a disaster. Why? Because the first time we called write, we have to resolve the library function and so on. There's a couple of ways to make this less painful, but what we're going to do is, instead of puts, we're going to do a write here. Fire, we're going to write to standard out 5-6 characters. Okay, then write will already be resolved. Next time we call write, we're just gonna boom, nice and fast. Okay, that means we need to obj dump it back out. Okay, we're right here now. That's where we want to break. Gonna disable breakpoint 1. Gonna break here, continue. All right, let's run it. All right, breakpoint. So now we step through. Boom, you see this right away, syscall. Okay, that's what we want to see. All right, so we're about to do the write syscall from our user space launcher application. When we do this, boom, we are magically in the kernel. Right? That's exactly what happens when you run syscall. You get shunted to the syscall entry point inside the kernel. Let's now break on too little too late. All right, we'll continue here. So this sec fault, right? Let's cat proc all sims. Shit, we need to be root for this. But without ASLR, they're the same between practice and non-practice mode. So let's now break at this device right and see what happens there. Okay, so let's run the launcher. So we have a breakpoint in the launcher where it calls right. Continue. Now we have a breakpoint in device right, the handler of our device, this right here. So this is where we're breaking. Now let's step a little bit and we'll see what happens. Or actually, let's next instruction a little bit. Uh-oh. I think I hit the bug. Okay, sorry. Next instruction doesn't always work when you're debugging the kernel. I thought they fixed this bug, but apparently I was wrong. All right, here we are. We step. So here we are. We're about to call copy from user. Okay, now we're in copy from user, which is exciting because we're about to copy in our shellcode. Let's finish copy from user. This doesn't work. Yeah, there's some frustration here. Okay, let's try this again. All right, firing, stepping. Actually, let's continue. Okay, we're in the kernel. Step instruction. Next instruction. Yes. Okay, we've stepped over copy from user. Yeah, you have to be careful about the use of step instruction, next instruction. Debugging the kernel is a little bit fraught with peril. In this case, I wasn't able to do next instruction from the very first instruction of the function. I have no idea why. Could be a Jeff issue, could be a GDB issue. So I instead stepped all the way to copy from user and then next instruction over that. As a reminder, the difference between step instruction and next instruction. Step instruction will step into calls and so on. Next instruction will do the call and then give you control instead of going into the call. Both will execute the call, but one will debug into it, the other one won't. All right, so we just did the copy from user. All right, now we're going to see this call x86 indirect thunk raw. What the hell is that? It doesn't show up here. Well, it actually does. It's how this is implemented. You actually see this is call x86 indirect thunk rax. It puts shellcode into rax and then it calls this function. That if you look up this function, okay, that's not the function. Nope. Okay, x86 indirect thunk rax. You can see what it does is you can get this very long description. It's basically something that will jump to rax. And in fact, we can walk through it and see. We do step instruction, step instruction, step instruction. Okay. What's going on here? We are jumping rax. So why don't we just do a jump rax? Well, this lfence is a very important instruction that I wish we were moving on to the architectural vulnerabilities module. Exactly, as Connor's saying, what's going on is some amazing foreshadowing. This is a mitigation for Spectre, the microarchitectural vulnerability that would allow, otherwise, given a pattern like this, unfettered control to read control to physical memory. All right, anyways, instead, we just jump to rax. Now, we are executing our shellcode. Doesn't this look familiar? We load instruction of this. Let's see what this is. Or we load address of /flag. We move RSI 0. We do the syscall to call open. But we're in the kernel. We're on the other side, on the wrong side of the syscall boundary for this shellcode, right? Step, step, step. We're about to call syscall. What is going to happen? Boom. We're back in entry syscall. So we got, our control flow got yeeted back into the entry syscall handler from a syscall handler in a way that the kernel completely doesn't expect. The kernel doesn't talk to itself with syscalls. User space talks to kernel space with syscalls. This isn't the shellcode you want. Once you have code execution in kernel space, you actually want to achieve very, very different goals. And those goals, for example, can include privilege escalation. I will point you. Let me open the lecture. Let's see. It's over here. All right. I mean, why am I doing this off camera? Let's just pull up the browser. pwn.college. Scroll up to the front. Go privilege escalation. Me with my long hair. And you can talk about privilege escalation. What do you want to do once you have control in the kernel? Once you have code execution, one of the things that you can do is find the struct that encodes the permissions, the credentials of your process, of the process that made the system call, and change the effective user ID to 0, right? To do that, as this lecture says, and please go back and watch this lecture because I'm pretty sure I actually demoed this end to end. Well, I'll double check right now. But there are two functions you need to call. You need to call prepare kernel cred to create a structure that defines credentials with user root, which is just if you call this with null, and then you pass that structure to the commit creds. So this is all you have to run. That's what your kernel shellcode is. Not open read write. Open read write is something you do from user space. From kernel space, you elevate your privileges, or you escape a seccomp sandbox, which you'll have to do next level. Or not next level, but in level 8. Alright. So, let's take a very quick look at... Oh, yeah. No, yeah. So go back, read this, and I actually do this attack nearly end to end, at least in source code. And of course, how do you get the shellcode out? Well, you can extract that shellcode and go with that. Yeah, I had a lot of hair when I recorded this. My original plan was to re-record everything this semester, but with me being constantly sick, maybe I'll re-record everything over the summer and have everything smoothly and you know, consistently recorded. So go read this, figure out how to do this. Let me see just how far I go in demoing this.
Okay, we are going to run our ioctl. So before it should be whatever you, or open it up in binary.
So I go through, I demo.
My home directory of my system.
I demo what happens.
Prepare cred struct argv0. Sorry, just make root.c.
Do I demo the extraction of the shellcode? No, okay. Oh, let's see what happens here.
There's a file called...
Okay, yeah. Read this whole thing. That's the net lecture you need to solve that challenge. Awesome. Okay, Question on Twitch, why am I sick so much? It's not COVID. I sent baby on to daycare this semester. And she's just been bringing back colds and stuff from daycare nonstop. Not COVID yet, but and I'll hopefully get my booster as soon as I recover from this cold, so get heavily more protected. But yeah, it's a brutal nonstop cold infections. All right, awesome. So that's level 6. I can see why that is getting people down, but it's good. You will soon learn to run awesome kernel shellcode, not user space shellcode in the kernel. All right, let's take a quick look on what else people are having trouble with. I'll probably have to run at the top of the hour, but we'll roll until then. Okay. Let's see. Scroll up. The code calls kernel when it is in the kernel, so it doesn't work. Yes, that's exactly it. That's exactly what's happening. Okay, been having issues with 7 and 8. Can't reliably get the correct address into RAX. Done it with the help of GDB in practice mode, but not in the regular levels. All right, let's take a look at 7 now. And we'll also do a similar sort of guidance for 7. All right. Launched up level 7. Let's copy it over. So there's a question on Twitch. Would a kernel ASLR would kernel ASLR make this harder? Kernel ASLR will make getting shellcode execution harder, not necessarily what you do after you have shellcode execution. Once you have shellcode execution, ASLR typically tries to prevent that step. Once you have code execution as an adversary, you're pretty powerful. Now, there are contrived hacking challenges that give you code execution in a completely randomized environment where you don't know where anything else is. But they're contrived. In the real world, once you have code execution in the kernel, it's game over. And there's only KASLR on level 10. That is completely correct. On the other levels, KASLR is off. What is the most different child beyond 6? So 7 builds off of 6. 8 is a different attack vector, so that's different, right? 8 is a different goal, exploitation goal. 9 is a different exploitation goal in a way. And 11 or 12 are the most different in that you're not trying to elevate privileges, you're trying to recover a flag. It's almost forensic-y. Almost. All right. Let's do 7. So we grabbed 7. Let's close it out. Close out 6. Open 7. All right, let's see what it is. Looks very similar, except where we have open ioctl release instead of open write release. So this is something we talk over ioctls with. We decompile this. Looks identical in that it maps some shellcode, and I bet this says welcome to this kernel module, which it does. Boom, welcome to the kernel module. Okay, we go to device open. Nothing. Device open returns 0. Let's look at device ioctl. So if you compare ioctl against 1337, you should at this point recognize that hexadecimal 1337 is, or sorry, decimal 137 is hex 539. All right, then we look at then we look at the arguments, and we see that the length of the argument has to be less than a page, less than or equal to a page. The command has to be 1337, the ioctl number. So we have the ioctl number and the arguments. And if you are confused about this, the concepts of ioctls here, where do I cover it? Where do I cover it? In kernel module? Yes. I cover it in the kernel modules lecture. I talk about ioctls. And you can play around, of course, by compiling your own modules, etc. But this ioctl handler is triggered by the ioctl system call from user space. So input-output control. I just call it, or people tend to call it ioctl. And you give it a file descriptor. That's the pwn.college, pwn.college file, or whatever file you're interacting with a kernel through. You give it the request ID, and then you give it some data that depends on the request ID. So for us, the request ID is, the command is 1237, and then the data, so this is user space pointer. It's a pointer into user space directly. It's copied from user. We seek 8 into that user space pointer, and we copy it to the shellcode buffer. Where the hell is the length? I think I just fucking up. Here, let's tell it. Keyword. Give me 3 keywords, please. Bad declaration. Syntax error. Oops, keywords. There we go. Okay, V4. V4 is the first. So this is a struct. Let's convert to struct. No. Create new struct type. All right, it did a good job detecting the structure. So this seems to be the size. Okay, the size is the first keyword, has to be less than or equal to hex 1000. Then we copy that amount of size. So this is our shellcode into shellcode. And then this is our pointer that gets called as a function. Brilliant. All right, and all of this gets copied from user space. So let's take a look at the structure that we created here. Struct user space pointer. Come on. How do I get the C version of it? Why the fuck did that? What just happened? Where are my local types? Local types. Yes. No. Fucker. Local types. And where's my struct user space pointer? No, I just want it in C. Okay. That's not what I want. This is still in structures. Right click. Just Just want to export header file. Thank you. Okay, don't include dependencies. Don't include either basic types. Okay, we have created the structure that we will need to pass into the kernel through a lot of pain. .ko.h. There we go. Whew. This is the structure that we will pass into the ioctl. Why does it? Okay. The ioctl as this third argument that it will parse. And our constraints are shellcode size has to be under hex 1000 and this pointer has to be point to our shellcode, that the address where our shellcode will end up. All right, this is obviously contrived just to introduce these concepts of kernel space pointers and stuff, but we're gonna do it. All right, so let's modify our launcher. To create the structure with the shellcode. So this is unsigned long in reasonable people terms. This is unsigned char. Okay, and here's our function pointer. Fine. All right, we get the shellcode. And now, instead of reading it into char shellcode, we have a, we can just, well, this isn't the pointer anymore. This is user space data. Okay. Let's just say struct pwn data. I like that, pwn data. Let's just call it pwn data. Pwn data t. Okay. We have struct pwn data t. Pwn data. Okay, and then we just read it into, we have pwn data dot size equals, read it into pwn data dot shellcode. Okay. And what, instead of writing, we're just going to ioctl. Ioctl pfd, the command 1337, and our pwn data structure. Boom. All right. So, and again, this will load arbitrary shellcode. I'm going to show you with user space shellcode, but that actually I'm just going to show you with a cyclic pattern because that's going to be a lot better. Pwn cyclic n8 128 to cyclic 128. Yeah, I'll show you with a cyclic pattern so that I'm not leading you astray. I'll leave the shellcode part up to you. Okay. Then what do we do now? What do we do now? Now we actually do VM connect here. Actually, first let's compile this guy. Okay. Let's include it just to make sure it doesn't like here not having header files could really fuck us up if it like truncates my pointer by accident. All right, there we go. VM connect, VM logs. Waiting. All right, so VM debug. Actually, first proc k all sims. Yeah, so Connor's saying right now, this you might notice it's a little slow sometimes. I wait and so forth. It's because we're doing full emulation instead of virtualization for these guest VMs. Because we don't have nested virtualization available in this environment. But in our new environment that we'll move to at the end of the semester, we will. All right, anyways, let's break here. As a reminder, proc_k_all_syms has all of the symbols where everything is loaded. This isn't available to you outside of practice mode, but the symbols are the same, or the addresses are the same unless KSLR is enabled, which it is for one of these levels. All right. Let's break at device open. So, no, sorry, shit. We don't want device open. Oh, that is Actal. Okay, device Actal. Okay, awesome. Let's do our launcher. Boom. We are at iactal, the iactal handler. So we compare the command, which is an RSI. Oops. Well, yeah. Against 1337, which we are correct. And then, just for completeness sake, in RDI is going to be, should be a user. Oh, sorry. RDI is the file pointer. In RDX is a user space pointer that the launcher prepared that starts with a -1. Why does it start with a -1? That's not good. Okay. Let's just hit continue. So something bad happened. Oh, because I didn't give it a file. Okay. So let me log one additional thing. Firing, pwn data. Let's log the address of pwn data. Awesome. Okay. We're gonna. Oh shit. The address of pwn data, not pwn data itself. Okay. Nope, wrong launcher. Launcher 7. Boom. All right. So we're firing. This is the address of our pwn data. If we look at RDX, the third argument to the iactal handler, it's the right data. And I, again, forgot to specify the shellcode. So that's the shellcode. Okay, now, so it's at a different location, of course, because pwn data is on the stack. The user space stack is randomized. All right, RDX. Oops, typo. Okay. First keyword is 80, hex 80, which is 128, which is the size of our cyclic pattern. Amazing. All right. Then we have the cyclic pattern. All right, amazing. Then hex 1000 into it because if you recall, oh, interesting. So Jeremiah suggests that you can run 2 GDB instances at the same time. One outside of the VM, debugging the kernel. One inside VM, debugging user space. I usually go far out of my way to try to make that the same GDB instance. Just debug user space from outside by compiling it without PIE and knowing the virtual addresses. But yeah, you could do that. I guess you could do that. Anyways, all right. One instance is easier though because of you can reuse the same scripts and stuff. Anyways, okay. What am I doing? I am here to look at the header file or the struct launcher 7.h. Why does it? Oh, launch 7.c. Okay. 4096 bytes. That's hex 1000. Right, that's one page. And at this location, oh, +8. This location is where we want to jump to. So I made a big error. I didn't initialize that to anything. That's what happened to have been in memory on the stack when that stack space was allocated. But we're gonna see what happens when we jump there. So let's step a little bit. All right, we check. We already checked the size. We're stepping through. We're about to call. Here we're checking the size. We were checking the command before. Okay. All is good. The size passes. It's less than hex 1000. We are about to go into copy from user. I'm going to step over copy from user using next instruction. Okay. We're about to call my shellcode. We load RAX from my the struct that got copied in from user. And and just for the record, when we copied from user, of course, we copied RDX was what we RDX is what was no, RDX got reused. RBX is where it got RBX is the user space, is my user space structure. RDX then moved into RBX at some point. I did copy from user. Why isn't SMAP preventing this, Connor? You wrote this in a way that SMAP should prevent. What Connor did here is very... Wait, Connor, this is my code or your code? Whatever. What we did here is we're using the function pointer directly from user space. That could be very, very interesting. Obviously a toddler 2 challenge. Is SMAP off? Does QEMU not support SMAP? That's possible. Let's take a look. QEMU might not support SMAP. TCG supports SMAP and SMAP. Maybe we have to configure it specifically. Maybe we have to emulate. What CPU model do we emulate right now, Connor? This is interesting. Yeah, I'm sorry for saying it. This is your code. I think I wrote that code originally, and I made that bug. Yeah, so I bet the default doesn't have SMAP and SMAP. Huh. All right. Yeah, so we're going to try calling into user space, seeing if that works, and then we'll try calling into the kernel. All right, so let's focus. So, RBX is where my user space struct is, and what I'm doing is loading the pointer from RBX plus hex 1008, that's my function pointer part of the struct, into RAX, and then calling RAX, right? And RAX at this point is some function pointer that yeah, that's the address of some function that was already on the stack because I never initialized this. Let's see what happens when we do this. Boom. We're about to jump to RAX. It works. Fucking QEMU doesn't support SMAP and SMAP. In the default configuration, at least. Alright, let's step once, you're right. Yep, happily stepping. Okay, ladies and gentlemen, we're executing kernel user space code in kernel space. So all of that stuff I was telling you about, that hey, in the lecture yesterday, that SMAP and SMAP are all enabled because we're not going to insult your intelligence. Well, here we are. We tried, but we, in an insult to our own intelligence, apparently QEMU needs to be configured. My guess is QEMU needs to be configured explicitly to support it. That's my guess. All right, anyways. I'm going to show you the correct way to start executing shellcode. And that is, of course, by utilizing the kernel, the executable kernel buffer that it got copied into, the same buffer as in level 6. And we're going to point this function pointer at this buffer. So let's make that happen. Let's see where that buffer is. And where that buffer is in RSI. Let's see if RSI is still... Nope, RSI is fucked now. Let's scroll back up. At some point, I printed out that buffer. There was a 616161 in it. Oh, no. Come on, give me my... There we go. Nope. Yes. No. It's in kernel space. All right, let's run it again. We'll continue here. We crashed our kernel thread, sec faulted our launcher. Let's try it again. All right, we fired the cyclic data. Wow. To enable SMAP, we add -cpu kvm64 SMAP to QEMU. Today I learned. The real question is, do we do it now? Or do we just tell people to assume it's enabled? All right. Yeah, I kind of think we should do it now. Anyways, as things are right now, you can jump to user space shellcode from kernel space, which is definitely unintended. Okay, so let's just look at it, how to do it the intended way. I re-triggered the ioctl handler. I'm going to step until we are about to call copy from user. Copy from user takes an RDI, the mapped memory address. Why does it already have all A's in there? Oh, probably from the last time we ran this. Yeah. All right. We're going to step over copy from user. Now, copy from user has... no. Okay. Sorry. Let's continue. Rerun this. Step. How do you find out where that buffer is? There are two ways to figure it out. One way, you look at you break at init module. Can you do that? No, you can't do it because it runs before you have debugging control. No, you could do it. You could do it early on. But let's just pull it out of the call to copy from user. Copy from user takes two arguments, RDI is where we're going to copy it to. RSI is where we're going to copy it from. And then RDX is going to be where how much to copy. RDX is 128. RSI is our user space address. And this is where the shellcode is going to go. Cool. Now what? That doesn't change if we continue. That is the shellcode that was the buffer that was allocated at the beginning of the module loading. And with KSLR off, it's going to be at the same location every time. It's going to be at this FFFF, that's kernel space, C9 00008500 in at least in this level. And every time, of course, you should check in practice mode what that address is, and then solve that in real mode. All right, so that's the address we want. Let's excuse me, let me blow my nose. All right. We want pwn data dot function pointer to point there. We compile it back out. Let's give it the correct conversions. Okay. We launch it. Now we're back in the iAxle handler, our good friend. And let's go see, we copy from user. And then we move our struct offset into what? Oh. We move this into REX. This is where our shellcode is. And when we do the jump to REX, boom, we are executing our shellcode. Awesome. So, to answer the question of how to figure out where to jump with my shellcode, look at where the shellcode, the allocated shellcode buffer in the kernel is. Now, for those of you trying to jump into your user space shellcode, don't do it. And if you did it, go back and do it the right way if you're interested in learning the right way. What am I trying to say? Go back and do it the right way, and then use the kernel addresses, which are, in this case, a lot more predictable because they'll be at the same place every time. Awesome. Okay. That should be enough for level 7. And then, of course, level 8 is a little bit trickier in that level 8 has your shellcode, your user space shellcode running inside of seccomp. So elevating privileges is not enough. So that'll be fun. You'll have to figure out how to disable seccomp, which I do in this lecture, and which you should adopt to your to your use case of shellcoding this. It'll be very fun. Cool. All right. So someone's saying, okay, for those levels, do we need practice mode to debug to get the shellcode address on the heap, on the kernel heap? Yes, you do. It's not actually on the kernel heap. You interact with the kernel heap using kalloc, which is not what we're using to initialize. This is an equivalent to mmap, but in the kernel. So it's in kernel space. It's not on the heap. It's just a kernel space mapped page. And this is what you want to get the address of. Awesome. All right. Thank you for joining for these office hours. Of course, anytime ask more questions. I'll do another office hours on Monday, and then we'll go on from there. On Tuesday, Toddler 2 arrives. Good luck.